we're doing sharpening, and we saw different filters to do sharpening, and then we started to think what happens with the noise. And we already were discussing what is the concept of color noise and white noise and the distribution of the noise at a particular sample. So this Gaussian, uniform, salt and pepper, they all refer to the distribution at the point, while the being white or not refers to the correlation between neighboring noise samples. And okay, and we started, we stopped here. So this is the appearance of Gaussian noise. And now you understand this Gaussian independently and identically distributed noise. So every point is Gaussian. That is the first word. This independent means that every point has a realization of a Gaussian random variable that is independent of all the rest. So it doesn't look at what are the nearby samples to take its value, and identically distributed. So that means that all pixels have the same distribution. And so let's say that the distribution is a Gaussian with this mean and this sigma, this standard deviation. And when you compute the histogram of your gray values, this is what you get. So you don't get a pure Gaussian, so a pure very smooth curve. The reason is that this is a random realization. So a random realization, just by chance, some of the values you have a little bit more of those values than from others. And this is the appearance of this Gaussian noise. And here you have the power spectrum. So the power spectrum, well, they're missing the square, but the square, well, it is important, but it is a linear transformation. Well, not linear, but yeah, if you forget about the one, the square here goes out, and you have 2 multiplied by the logarithm. So that is why I said it is linear. So this is simply scaling. And the plus 1, why do we need the plus 1 there? Why do we need plus 1? Sorry? Yeah, to avoid the problems at 0. So at 0, this the logarithm is minus infinity, and if there is a point or a frequency at which there is no energy, then you will get a strict 0, and then you want to avoid this minus infinity. So you add 1, and so it is a very small addition. And this is the power spectrum, and this is the autocorrelation. And you see that the autocorrelation has been computed in this way. So actually, to be correct, you need a square here in the module. So module squared is the power spectrum density, and then if you do the inverse Fourier transform, then what you get is the autocorrelation. And the real part is simply to avoid numerical instabilities. So in principle, that should be a real number, but because of the numerical calculations in the computer, sometimes you get the imaginary part like 10 to the minus 16, and you don't care about those imaginary parts. So it looks like a delta. So a delta means exactly this, that each pixel is independent from the rest. Okay, so what is the problem with sharpening and noise? And we saw it yesterday, that the sharpening may also boost the noise. So let's say some examples. So for instance, let's say that we have this image, and we have this noise image. Okay, so let's go here. Go. Okay, so let's say that we have this model, x plus n. So this is the ideal image, this is a noise image, and those were the two images that we were looking in the slide. Okay, so this is x, this is n. And then let's plot the power spectrum of the two. So this is the power spectrum of x, this is the power spectrum of n. You know that the power spectra, they are two-dimensional functions, but we are making a profile, we are taking a profile along one of the directions. So let's make a plot of what we are doing. So the Fourier transform of this is a two-dimensional function, but we are taking this line and plotting what is happening on that line. Okay. So the spectrum of the signal, the spectrum of noise. And the spectrum of the noise, you see a peak at the origin. So what does that mean? Why do we get a peak at zero frequency? Because the mean is not zero. So the mean is different from zero, and then what you are seeing there is the mean. So at zero frequency in the Fourier spectrum, what you see is the mean of the image. Okay, so, but otherwise it is relatively flat. And again, when you look at the particular realization of a white noise image, so this is a white noise image, in the same way that we had here a histogram that was not a pure Gaussian, what we get in the Fourier spectrum is a spectrum that is not purely flat. So it is purely flat. It will repeat this process of making many images of this kind, and then taking the average of all those power spectra. Actually, if you remind the power spectrum, so the power spectrum was something like this. So let's say, let's do it in 1D. Okay? So it is the Fourier transform of the autocorrelation function of the signal n. This is the lag. Okay. So, but what is the autocorrelation function? So, the autocorrelation function is the expected value of n evaluated at n and evaluated as n plus n. And this thing here means expectation means if you want to do it numerically, what you have to do is run this obtain many realizations of these random variables and then taking the average. So this one is flat. This one is flat in the Fourier space, and this is the result we all know. This is flat when you have taken the expectation. If you take just one random realization, it is not flat. It is you get some noise around it. It can be rather rough, this noise. So depending on what is the size of your sample, it can be rather rough. But it can be something like this. So this is something very useful to think of. So this wide spectrum is only obtained after averaging. It is only obtained on average. Okay, so only after averaging a lot. Okay, but then we compare these two spectra. So these two spectra, when we add them together in the images, so this would be the spectrum of X plus the spectrum of N. There is a property spectra. So in general, so we are here. Okay, so in general, the spectrum of I is not this one. In general. So you add two signals, the spectrum is not the addition of the two spectra. But so this is in general. But if X and N are independent, then they are together. So, but this is only if X is independent of N. Okay. And then the spectrum of the output is the addition of the two. But in general, it is not true. So it depends on whether what is the relationship between. Okay, so this is what we are seeing. So now we are seeing X and the spectrum of X, the spectrum of N, and we see that at some frequencies we have more power coming from the signal, and at some other frequencies we have more power coming from the noise. So somehow beyond this frequency, the signal-to-noise ratio is smaller than 1. Below that frequency, the signal-to-noise ratio is larger than 1. So the low-frequency components, we see them well. The high-frequency components, they are embedded in noise. Okay, so here we have the same idea, but now in 2 dimensions. So now these are the two power spectra. So this is the original image. This is the one of noise. So this is X. This is N, and this is the addition of X plus N. And here we have painted in blue those points for which we have more noise than signal. So the signal-to-noise ratio is smaller than 1. And in red, where we have signal-to-noise ratio larger than 1, and these are both together. And because this is a simulated example, we have we know for which coefficients we have more signal than noise. But in reality, you never know. The concept still applies, but in reality, you don't know for which frequencies you have more power coming from the signal than power coming from the noise. Yeah, so let's see what is the effect of this boosting on the different when you have images with noise. So let's say that this is your original image, this is your image with noise, and this is the sharpened original. This is the sharpened noisy image, and we can make a zoom. So for instance, this is the original image, this is the noisy one, and these are the sharpened ones. So sharpened original, sharpened noise, and especially here in the background, you see that you have a lot of noise compared to this one. So where you have a lot of details, so let's say that you have a lot of details here. A lot of details means a lot of power. So you have a lot of power coming from the signal. But where you don't have many power, so here you don't have much power coming from the signal, for instance, then what you see is mostly the noise. Okay, so this is the same concept, but now in real space. So in that particular region, the power coming from the signal is very much concentrated at the origin. We don't have high frequency components. So if you just compare, if you just look at this region, we don't have much power coming from the signal. So what we are boosting is the noise. And the same happens in this other area, but now it is the opposite. we have much more power coming from the signal, so that is why we still see all these details. Okay, so yeah, so sharpening, if you have noise, it's not such a good idea. So somehow you have to balance between boosting noise and boosting the signal. And here we have the same, but now with this image that we know. So this is the same image we had before, but now with noise. This is the power spectrum, the enhancement. So this is the high pass filter. And again, in those very flat areas, what you have is very little power coming from the signal and a lot of power coming from the noise. And then what you are boosting is the noise. You are finding the derivatives of the noise. And then the sharpening of these two. And we can, so this is with linear enhancement. So here we have omega, while this one is with quadratic. So we have omega squared. Any question? No questions. Okay, so otherwise we move to the next topic, that is pixelization and quantization. Okay, so we are already familiar with these two concepts. So pixelization is, for instance, this effect that is used to hide identities or to hide whatever information you want to hide. It is very much related to sampling, as you already know. So pixelization, let's say that this is our ideal image. Now it is in high resolution, so meaning that it is digital, but we have a sampling rate that is much smaller. And then we want to produce from this image, we want to produce another one that is also digital, but it has a bigger pixel size. And we will see one possible technique, it is not the only one. And the quantization, you already know. So pixelization, you can think of it as sampling in a space. Quantization is sampling in the gray values or in the intensity values. So it is, instead of having so many colors, having a much smaller color range, or better said, the gap between one sample and the next, but in the color space, is now bigger. It is the same here. The space between one sample and the next, but now in real space, the spatial domain is much bigger. Okay, so this is the same effect, one in colors, the other one in space. Okay, so all these ideas we already know. And we will introduce this somehow this a possible way of doing this pixelization. So let's say that we have a digital image. So for digital images, the notation we are using is square brackets. So those two are indexes within the matrix. And then we will produce an image, an intermediate image that is called the downsample image. And if you look at the formula, what it says is you take neighborhoods of size delta and you average them. So you are going from, let's say, make it here. Okay, so let's say I have this image, this 4x4, so original, this is the high-res image. And then I'm making a downsampling by factor 2, so my delta is 2. And now what I'm doing is I'm taking all these pixels and computing the average. And this will be one of the pixels in my output. And the same here, the same here, the same here. So now what I have is an image that is 4 by 4. And the pixel size is bigger. So if we denote by TS, the sampling rate in one dimension, in the original image, the sampling rate here is 2 TS. And this is TS prime. Okay, so yeah, actually, I think a better representation would have been like this. So this is this, and now a better representation would have been like this. So it is of the same size as the original, but now TS prime is 2 this. Okay, but my image is 2 y. Okay, so this is what this is saying. Okay, so you are taking an average, and since you are taking an average of 2 times 2 pixels, you have to divide by delta squared. And then these limits of the summation is simply saying who are the pixels that are taking part in the average. This I think it is much more clear in the figure I did. And then the pixelated image is the downsampled image, but now upsampled by a factor delta. So you make first a downsampling by a factor 2, and then you make an upsample by a factor delta. So the process of upsampling and downsampling are familiar to you. So you know what the downsampling and upsampling is. Okay, so yeah, so yeah, this is it. So there's nothing really special about it. So the thing is, we have an image that has. This is a discrete image. This is not continuous image. So that is why we're using sums. We are not using integrals. Yeah.
The downsampling something and the upsampling are they the same?
Yeah. That's the upsample and downsample factors. Here in this example, they are the same, but they don't need to. Okay, so we have a digital image, and in this digital image, we are saying, okay, I'm taking all these delta times delta pixels, and then I'm computing the average. And from where to where? Okay, so yeah, let's say that I want to produce the RC pixel in the output. So the RC pixel in the output, they come from the rows R times delta to R plus 1 times delta minus 1. So that means relatively easy to see. So let's say that we are doing a downsampling by a factor 2. Okay. And we start with our rows and columns starting at 0, 1, 2, 3, 0, 1, 2, 3. Okay, so and we are doing by a factor 2. So the pixel 0, 0 in the output, this is R, this is R. This is C. Where is this coming from? Okay, so pixel 0 is coming from this corner. Pixel 1 is coming from this corner. So actually, I have, if I'm going 0, 1, 2, 3, 4, I have to go in the original like 0, 2, 4, 6, 8. Okay, so I have to go in steps of 2. Okay, then, so I have to go from delta R to something. Okay, so who is this something? So something very relatively easy is to say, okay, so you're going from delta R to delta R plus 1. But if we think of that, that would mean that to compute the pixel 0, I also including 0 plus 1 times delta, that is pixel 2. So I would be going 0, 1, 2. That is not what I want. I want to go 0, 1 only. So minus 1. So very easy. From here to there, how many rows we have? From delta R to that thing. How many rows we have in between? Delta. We have delta rows in between. Okay, and the same for the columns. Now we understand these limits here. Okay, so yeah, and this is important again. So my downsample image has also indexes 0, 1, 2, 3, but now they represent in the continuous space. In the continuous space, they represent the same area as my input. But in number of samples, this is 0, 1, while this one was 0, 1, 2, 3. Okay. So they have the same size because we are plotting at the same time the continuous space. So the continuous space is somehow underneath. That is why they occupy the same. But otherwise, this image is twice smaller than that one. In the discrete space, in the discrete indexes, this one is twice smaller. So yeah, and then we have the sample. So yeah, this is just the process of making this average, and then when you do the upsampling, you are substituting all these pixels by the average. So all those pixels become take the same color. Yeah. So yeah, this is a little bit more of these details, but yeah. This is what is the size of the downsample image, and then it is, if you are doing by a factor, a downsample by a factor s, then it will be number of rows divided by s times the number of columns divided by s. Now you know this notation. This is rounded to the floor, and then you have to compute those means that are the ones going from rs to r plus 1 s minus 1. That's fine. And then the upsampling, for the upsampling, it is similar. So you have the same size as the input, and then the upsampled pixel at the location rho chi b is the value of the downsample image at RCB for all the rho and chi's in this neighborhood. And this neighborhood is this one, that you identify the same kind of elements. So you have to multiply by s, so you have to go in the steps of s, and then you go from rs to r plus 1 times s minus 1. So it is the same. Okay, so here we have, for instance, let's say that we have an image and we are making a pixelation by constructing pixels or squares of size 256, 256. So this 8 means the level of pixelization we are doing. Okay, but the box size is this one. And then this is a little bit less of pixelization, and then a little bit less, a little bit less, a little bit less. At some point, you don't notice almost the You see, from the original to the first level of pixelization, you don't notice. And the reason is that there has been some low-pass filter in the process of constructing the image to your eye, to your brain. So it could be either the computer, can be the projector, it can be your eye, can be whatever. But you barely see the differences. Maybe here in the borders you see a bit. It is not easy. But then when you start to make bigger and bigger pixels, at some point you clearly notice. Okay, so what about colors? So in colors, we can have also sampling. So we can go from 16 million colors. So 16 million colors, where this number 16 million comes from? This is a magic number. 2 to the 24. Yeah, 2 to the 24. Yeah, that is a just you're engineers. You have to be very familiar with powers of 2. So, for instance, 2 to the 24. This is the same as 2 to the 4, 2 to the 20, and this is 16. This is approximately 1 million. It is not exactly 1 million, but it goes to 1 million, more or less. What about 2 to the 14? What is it? For instance, if it is bytes, this is exactly 16 megabytes. And 2 to the 14, so this is 16 kilobytes. This is 16 kilobytes. So 2 to the 10 is approximately 1,000. The other one is 2 to the 34. $16 gigabytes. And what is a giga approximately? It's very easy. This is 10 to the 3. This is 10 to the 6. So a giga is 10 to the 9. What are the next ones? Terabyte. 44, 54. So this is 16 terabytes. That is 16. What is the next one? Petabyte. This is 10 to the 12, 10 to the 15. You know how much data generates an electron microscope per day? 2 terabytes per day. So, yeah. Okay, good. So this 16 million colors is because we have 3 bytes for the colors, and then we can represent 2 to the 24 colors. What about these 16 colors? How many bits do you need to represent a color? 4 bits. Do you remember yesterday in the paper how many bits per pixel they had when there was a compression? 0.38. So this is 4 bits per pixel. Yesterday we had 0.38 bits per pixel, so 10 times less. Okay, so yeah, if we go from 16 million to just 16 colors, it clearly we cannot represent these as smooth transitions. They have to be stairwise. That is what we see there. It goes in steps. And here we have more or less the same representation where we have the input intensity, that is a continuous value, let's say with 8 bits from 0 to 255. And then in the y-axis, we will transform an input value like this into a constant value. So all these values, all these delta values, if you will, so all these delta values will be substituted by this value, a single value there, then all this delta by another one, all this delta by another one, by the average. We are doing the same process that we had before, but before, sorry. Before we had it in a space, but now we have it in color. So we are also computing the average. Now it is not a double sum, it is a single sum. So we are computing the average of all those colors and divided by delta. So computing the average of those colors. And like that, we compute our transformation function. This is the lookup table that we saw in the point processing lecture. So this is the input, this is the output, and this is your lookup table. And here you have the effect for different kind of quantization steps. So if your delta is 2, then instead of 256 levels, now you have 128 levels. And you barely see the difference again. Now this is with delta 4, delta, so this is delta 2, delta 4, or this is delta 5, 8. We are going in power of 2. Actually, if you think 256 is 2 to the 8, 32 is 2 to the 5, so the difference is 2 to the 3. So the delta here is 8, it's not 5. Okay, so delta is 2 to the 3, delta is 2 to the 4, 5, 6, and 7. Yeah, at some point we really see the differences. At the beginning we don't see the differences so well. And here we have the different lookup tables. So this is with 8 bits. We have almost a continuous. So we know it is not a continuous, but we cannot see the steps between one and the next. And then with 7 bits, 6 bits, 5 bits, and so on. And you know, this gray value here, it is the average of all those. Okay, so let's say that we have an original image and we can perform different operations on it. So we can do this contrast enhancement, this dark enhancement, bright enhancement. And this is with 8-bit images, and this is with 16-bit images. And yeah, you can, this dark enhancement and bright enhancement, we have not talked about those two specific operations, but you can very easily imagine what they are. The contrast enhancement, we know the way, right? The contrast enhancement. This is the one of high today. So it is the one that takes the minimum and maximum and maps it into 0 to 55 and computes this transformation. This is x, this is y, and y is a function of x. And this function that we were seeing at the beginning, this was one of our first lectures. we call it lookup table. Okay, so this is contrast enhancement. What about dark enhancement? I want to construct a transformation that highlights or makes more differences in the dark region. I will use the same. What can I do?
Same like getting a lower range.
It has to do with the slope. So where the slope of the transformation is larger than 1, I will enlarge the dynamic range there. So I can do something like this. This one, the dark region, has a high slope, so the dark values become separated. And the high values, they have to collapse. There is no free line. So if you are giving this range to the dark areas, then you have to sacrifice the white areas, the brighter areas. So this would be dark enhancement. What about bright enhancement? I want to highlight the bright areas. This is second, but now we are in direction. So now the bright areas become separated, and you are sacrificing the dark areas. So this would be bright enhancement. Okay, so let's make a break. So this is just an illustration of these operations done with 8 bits and with 16 bits. There is a difference between doing it in 8 and 16 bits. So in 16 bits, we have similar plots, but now we have similar plots. Minimum and maximum. But now it is between 0 and 4. To 55. If I do it with 16 bits, two to the 16 minus 1. This is actually 2 to the 8 minus 1. What is this number? You have to be familiar with it. Okay, so we have already encountered one interesting idea, that is that the plot will be similar and everything will be similar. But the number that we have in the matrix, in an image, is arbitrary. So it depends only on what is your scale. So if you represent it with 16 bits for every channel, now your numbers are much bigger, but that doesn't mean that the image is much brighter. So this is not 200 times or 256 times brighter than this one. So it is the same kind of brightness, but only now represented with a different number. So what is important in an image is the relationship between relative regions. So if a point here, so you have an image. So when you are going from 0 to 255, and you have here a value 100 and here a value 100, so that means that this pixel is twice brighter than this one. But if you have the same now with 8 bits, with 16 bits, sorry. So instead of having those two values, you would have the same value, and now multiply by 256. And it doesn't matter. So the difference is much bigger, but what is important is the ratio between the two, not the relative, not the absolute value of those numbers. So numbers in images, they're arbitrary. Depends on which scale you're representing your colors. And this has to do with something that you already know. That is, what is this? You have done this in practice. An analog to digital converter. So whatever camera you have a response. So here you have intensity, and this is number of photons. And here you have a number, and this number is arbitrary. So you have a converter that converts, for instance, let's say that it has a response, something like that. So normally you like to work in this area or in this linear. And then you set the zero at this point, for instance. And then the maximum at that point. And what is this maximum? Actually, you don't care. So that number is arbitrary. What you care is what is the step? What is the step that I can represent? How many steps I have going from zero to maximum? And here it comes these ideas of having, for instance, 8 bits, 12 bits, these are typical values, 16 bits. So what you care is, what is the size? How many steps can I represent between my minimum and maximum? And typically, in any physical device, you'd like to work in the linear response area of that physical device. So you wouldn't like to go much further to here, for instance. You wouldn't like to go to here, because all these values you cannot separate well. So this area is so flat that you cannot distinguish how many photons have arrived. So you want to work in the linear area of the device. So the number that we have is given by some either by some physical device, or it is arbitrary. You load any image from the internet and it has value between 0 to 55, but those are arbitrary. Okay, so here we have those 3 operations performed with 8 bits and 16 bits images, and we don't barely see any difference. And for instance, we can look at the histograms. So for instance, when you have this is the original image in 8 bits, this is the original in 8 bits, and then we go with the different operations on 8 bits. So here we are stretching, and because of the stretching, we are creating these holes. Here, this dark enhancement. The dark enhancement, we know that the holes are related to slopes larger or smaller than 1. These holes here. Slopes larger than 1. We reasoned this in the first lectures. And these spikes, they are related to what? Slopes smaller than 1. So if the slope is smaller than 1, it may be that 2 values at the input collapse into the same value at the output. And so these spikes are because of slopes larger, smaller than 1, holes created by slopes larger than 1. And then now we do the same operations, but now with 16 bits. And because with 16 bits, we have many more values to represent. Now we don't have those holes, but now it is more like continuous. So my input here is between 0 to 55, but my output is much bigger. So I don't have those holes. So the quality of the 16-bit operation is a bit better than this one. But the difference is not very much. So when you look at the images, you don't see those differences. But when you look at the histograms, you see that this one creates holes, which is unnatural for an image. This one has continuous values, or continuous histograms at least. And here you have a zoom of that area. So this is the original image, and this is the zoom. And then this is the enhancement with 8 bits, and enhancement with 16 bits. This one doesn't have those holes. So in principle, it has a smoother transitions. And for instance, here you see a little bit of better contrast than there. So not so much. How many more values do you have for when you go from 8 to 16 bits? So between one color in 8 bits and the next one, I have just one possible value. Between those two same colors in 16 bits, how many colors I have in between? 256. 256 between one step and the next in 8 bits. So you take two colors in 8 bits, and now you take those two colors in 16 bits. Now you have 256 colors in between. Yeah. So, for instance, let's go to it. So, let's say that I have in 8 bits, I have the colors from 0 to 255. And I know this is black, this is white. And now let's consider the difference between the 254 and the 255. Okay, so now with 6, this is with 8 bits. Now with 16 bits I have here, but now this is 65, 5, and this is white. 0 is still black. If you want to convert the color from this scale to this scale, it's not a good problem. This is a better problem. But this is number, so this is X, this is Y. What is the corresponding color in Y? 56 multiplied by X, right? Okay, so now let's consider starting the reasoning with 254. I think it is much better. What is the corresponding of X plus 1? So the corresponding to X plus 1 is Y prime, that is 256 X plus 1. This is 256x, that was the previous column, plus 256. So between those two colors, now there are 256 colors in between. Okay, so yeah, this is the enhancement with 16 bits, with 8 bits, And this is just to show when you move from one to the next. This is just to show that the difference is really, really small. But at the level of histogram, because of you have many more colors in between, you can have much better results. So much smoother values. Okay, then okay, so now we have encountered the concept of beats in the images. So yeah, what is in the lower 8 bits? So let's say that I have this image in 16 bits, and then I take so. So let's say that you have an image like this, so it has many pixels. For every pixel you have two bytes, the upper byte and the lower byte. And now let's make the lower byte with different colors. So we have the lower byte and the upper byte. And the same for all pixels. So like this, I'm representing my images with 16 bits. Okay, so now I separate in two images. One with the upper bytes, and another one with the lower bytes. Which one would you say it would be more significant? The upper one. So the important information should be here, not here. Okay, so let's say that is true. So we take this image that has 16 bits per pixel, we take the lower byte and we make another image, and this is what we see. So most of it is noise, except for a small region here, where it has significant information. But most of it is noise. And then we can use this fact for something that is called steganography. And actually the paper yesterday was a bit about this watermarking. So we are going to hide information in an image. So let's say that we take this image and we can dice it. Originally it has 8 bits per pixel, but now we represent it with 6 bits. So that is a very easy, so this is the 8 bit per band original, and this is the 6 bit quantized. So that is a very easy way to do that. That is so we have your image. So at this location, we have let's say 8 bits. So we have the bit 7, 6, 5, 4, 3, 1, 0. So this is the most significant bit. This is the least significant bit. Depending on where you're coming from, B0, B1, B2, B7. Okay, so and in principle, I'm using all of them. So let me. B7. So the color, let's say it is the color I'm represented there is 129. So 129 will be 1, 0, 0, 0, 0, 0, 0, 0, 1. Okay, this is my color there. But now I take the last two bits, whatever they are, and I suppress them. So I set them to 0. So now, in my colors scale, I'm going from 0 to 255. But which are the possible colors I can represent? Can I represent 0? Yes, it is 0, 0, 0, 0, 0, and then the last two are 0. What is the next color I can represent? 4. So the next color I can represent is 4 because it is 0, 0, 0, 0, 0, 1, and then 0, 0. What is the next one? 8. That is 0, 0, 0, 0, 1, 0, 0, 0. So you're going in steps of 4. 4 because this is to the 2. And you have decomposed your 8 bits. So you have your 8 bits, you have decomposed into 10 to the 6, 10 to the 2. So you are going in steps. You are going in steps of 2 to the 2. And how many levels do you have? How many different colors here? 2 to the 6. So I can represent only 2 to the 6 colors before I put 2 to the 8. But now my step is of size delta. Actually, the last color I can represent here would be something like 2, 3, 1, something like that. 2, 3, 4. So I cannot, in my new system, which I have the last 2 bits, they are always 0. So in my new system, the last color I can represent is this one. Okay, so now I have an image that the last 2 bits are always 0. So this one is the original. This one, the last 2 bits of all colors is always 0. Yeah, this is the histogram of the original. This is the histogram of the quantized one. What is the gap between one bar and the next? How many values do we have in between? 3 values. So you have a color, then 3 gaps, and then the next color. It is like from 0 to 4, you can represent 0, you can represent 4, but you cannot represent 1 to 3. So you have 3 values in the gap. Yeah, this is that information, that representation. So our colors now, they have the first 6 bits with some information and the last 2 bits without information. And an easy way to represent that in a computer is that you take any number, and let's say I have a byte, and I want to take that byte and get this value. So I want to set the last 2 to 0. So what you can do is right shift by 2 positions. So now everything is shifted to the right with 2 positions, and there are 2 zeros appearing. And then you left shift by 2 positions, and then you leave whatever you had at the beginning at the origin, but now you have 2 zeros at the end. Yeah. So this is an easy way of making this. So if you right shift by 2 and left shift by 2, the last 2 bits are 0. Okay, so what if I do right shift by 6? So I take another image, I do a right shift by 6. So a right shift by 6, how many bits am I keeping from the original? 2. Okay, so let's make this a little bit slower. Okay, so let's say we have 2 images. We have image 1 So let's start with image 1. So image 1, originally, it has all these bits. B7, B6, B5, B4, B3, B2, B1, B0. So this is original. Now I do right shift by 2. So if you do by right shift by 2, now you have 0, 0, and then B7, B6, B5, B4, B3, B2. And the last 2 bits are for free, so there's that one. Now we do left by 2. So now we have B7, B6, B5, B4, B3, B2, and then 6. Okay, so now we have another image that will be I2. And for not mixing things, let's call the bits B7, A6, A5, A4, A3, A2, A1, A0. Now you do right shift by 6. So you right shift by 6, so you have 0, 0, 0, 0, 0, 0, and then A7, A6. Very. And now I can take this byte, I can take this byte, and I can compute something that is, what is this operator? What is this operator? An XOR, an exclusive OR. So the exclusive OR, this is something or 0, or exclusive or 0. So that is something. So what I have is A7, A6, A5, A4, A3, A2, because I'm doing the OR with zeros. And then these two, they are also making the OR with zeros. So now we will have A7, A6. And this is our new image. So our image now has information from the first one, but also has a little bit of information from the second one in the last 2 bits. Okay, so this is what is represented here. So here we have in the same image, so we started with 8 bits. So this one is 8 bits. This one, the last 2 bits, has 0, 0. This one, the last 2 bits, has information from image 2. But you don't see image 2. So you are mostly biased by the information in image 1. So let's say that I want to recover image 2. So you have this one. So you're clever people. How would you recover image 2, the information from image 2 from here? What is the operation I have to do to recover image 2? Left 6. That's it. If you do left 6, now what we have is A7, A6, and then 0, 0, 0, 0, 0, 0. And now we have image 2, whatever is left from image 2. Okay, so we do left shift, and then what you get. So that was a hidden message in the original image. not in the original, in this one. So in this one, we have hidden this information. So this hiding is called the Steganography, or yesterday we saw it like a watermark. So for instance, what do you think of this watermark as a how sensitive it is to noise, how sensitive it is to how resilient it is to noise, to JPEG compression, to cropping. For instance, what about cropping? Is it good? Yeah, it is very bad for cropping. If you crop part of your image, you are losing that information. What about noise? So noise will be very bad to this kind of watermark. What about JPEG compression? Same. This doesn't have weight enough to be resilient to JPEG compression. So yesterday we saw a much better way. But this is a very, very simple way. It is very surprising because you have mixed two images in the same space domain, the same spatial region, and you don't notice. And what about if we do it with 4? So okay, maybe the last 2 bits is not enough. Okay, so let's put image 1 with 4 bits, image 2 with 4 bits. Is it much better? So here we have the original image. This is the one with 4 bits. So the last 4 bits are 0. So we have lost a bit of the contrast, but not so much. Now we are adding the second image with 4 bits. And again, we don't see it. The last 4 bits are occupied by something else. And you don't see it. And this is this something else. So it is really, really surprising. Okay, so next. Okay, so let's say that we have images of 16 bits. So now that we are familiar with this concept of bits, we may select areas where we have dark and light regions. So dark and light regions, in terms of bits, what does it mean? Yeah, so upper byte and lower byte. So you take the first 8 bits and the last 8 bits. And so you could take the region. So now in the dark area, apply an operation. In the other image, you apply a different operation. And now you combine the two. So you're not constrained to these lookup tables that we had before. So we have these lookup tables here. So we had these lookup tables here. You're not constrained to do it on the numbers as they are. You can separate. You can separate into the upper and lower bytes. And then this is the dark image, this is the bright image. So this is dark, this is bright. So here you would like to do bright enhancement. Which one is that? If I want to do bright enhancement, yeah, this one. Here I want to do dark enhancement. So I can do this one. And now I can combine the two. So I can combine this one here, this one here, and produce a new image that has these upper bytes and these lower bytes. So you can be really, really creative. you can think of many different ways of working with your signals. Now, you don't have to sacrifice anything. You have the best of both ways. So you have the best of dark enhancement and bright enhancement without sacrificing anything. But you apply the transformation to different areas of the image. And here comes another surprising idea. That is, we have always seen that noise is bad. Okay? Maybe that for some particular operations, noise is not bad, it is good actually. Okay, so this operation is called dithering, and we saw it a bit when we had at the beginning here. We had this quantization. So we start with an image, and then let's say that you quantize quite a lot, and then you start to see these artificial borders. Okay, so there is no border here in the cloud, in this region, and this one, and this one. It is only because of the quantization. But what if I introduce noise? Okay, so if I introduce noise, then that border doesn't exist anymore. So it is this one. So a possible strategy could be the following. So you start with your original image, you introduce some noise, you have to control what are the noise levels. And then the noise image is the one that you quantize. And yeah, what is the noise level? So normally you put 0 V, so you don't want to shift your gray values. And how much noise? So what is the standard deviation? So let's say that the input has a maximum value m, that typically it is 255, and you are going to quantize with q bits. So the output will have q bits. So a sensible value for sigma is the maximum divided by q by 4 times q. Okay, so let's see the effect. So this is the image with 8 bits. This is the same image with 4 bits, and the same image with 4 bits plus noise. So with 4 bits, we don't really see. Now let's see with 3 bits. This is original. This is quantized with 3 bits and quantized with 3 bits plus noise. And we start already to see here in the face these artificial borders. But now with the noise, we don't see. And this is with 2 bits. This is exaggerated. Okay? But these borders here, they don't exist in the real face. And with 2 bits plus noise, we don't see those borders anymore. How many bits per pixel do we have here? 2. Because the noise was introduced before. The noise, so you have the image plus noise, and then you quantize. So introducing noise, this is called dithering. It is not such a bad thing. You see, even with 1 bit, this is terrible representation. But 1 bit plus noise, okay, it is not good, but it is not terrible. It is not that bad as just 1 bit. How many? Bits. So it has 8 bits. Yeah. So it is performed, the operation is performed at the same level as here. So it has the same amount of bits as this signal. Yeah.
It's 2 bits per color channel, or
2 bits in each one of the channels. Yeah. So, but this is surprising. So adding noise makes can have some use. Okay. Any question? No? Then we continue. So if you don't stop it. Okay, so next topic. So next topic is let's annotate some practices here. So yeah, we have leveling. We have Steganography. And what else do we have? Yeah, this. I think this is good. Okay. Okay, so next topic is about sampling. So sampling is so just before going, yeah, let's see the problem, and then let's try to justify it a bit more conceptually. Okay, so let's say that you have this image. This is the high resolution image, and now you do downsampling, and with this downsampling, you get this image. So this one goes to this one, and then we expand it back to have the same size as the original. And you note that this lattice here, so this grid here, they have a different pattern. Can you see? So this is not the true pattern of the original image. So what is this? You already know this effect. It is called aliasing. So we have aliasing, and so let's see where the aliasing comes from. Okay, so let's remind in one dimension what the aliasing is. Yeah, I will create a new. Okay, so let's say that we have a signal. This actually that is a continuous signal. Okay, and now I want to quantize it, to sample it. So when you have a signal, this is not the best. So I have an input signal. So what do you need to quantize this or to sample it? What is the first operation I have to do? I have to multiply by a train of deltas, right? So I have to multiply like this. And so I have to multiply by this pulse of this train pulse. So this signal here is a pulse train. And the separation of any two samples is called Ts. And then this is the multiplication of them. So this one here. This one here. Those are actually the multiplication of them. Or the multiplication of the blue one with the black one. So that is why it follows the shape of the black one. Okay, so next. What is the next operation? Sorry? Yeah. So I need to convert it to discrete. So this signal now is converted to a discrete axis. Now the axis is n, it's not time anymore. And then I have this is x of n is equal to x of n yes. So this is n0 to 1 to 3, and this height here is the same as this one, is the same as x at 1 times yes. So this is one. That one is close there. How many? Bits. At the moment we are in a continuous level. So in a continuous, so you know a signal is a function. So this function here goes from set to I. So this one is continuous. That one is continuous. So we don't have this. So we are discrete in time, but continuous in values. Okay, so this is a reminder of what sampling is. So let me see how much time we have left. 4 minutes. So I think we can stop here before going into Fourier. Any questions so far? Actually, let's see what is the way back. Okay, so now I have my discrete signal, I have x of n, and I want to recover, the this instead of DC, let's call it continuous to discrete. So what is the first step I need to do? Discrete to continuous. So at this point, what I have is this signal that is continuous, that is defined in continuous time. I was to say something. Yeah. This you already know, but these deltas are called Dirac's deltas. So these are Dirac's. And what about this one? Kroneker's. So they have different definitions. They have very, very different definitions. Okay, so now I have this one. What do I have to do to recover my original signal? The low pass filter. You need the low pass filter with frequency, and now you recover your original signal.